Hello, this is Dr. Mohammed, and this is a new video for the design of steel structures according to AISC. And today I'm going to talk about the tension members. Today we're going to cover part 1. There are other parts. We're going to cover different topics under tension members. And today I'm going to talk about the tensile strength of tension members. The main contents for today's video is going to be related to, first I'm going to give an exposure to steel construction manual, some important hints and the different parts under this manual, and after that I'm going to talk about the introduction to the tension members, and then I'm going to go into the details of the tensile strength. Okay, let's go now to the first part, which is related to the steel construction manual. And whenever that we are going to talk about the steel construction manual, we need to know that this manual actually is it is important for any designer to have. We're going to talk about, of course, we are talking about the American Institute for Steel Construction, and in the same time we are going to work based on the specification or ASIC specification. This requires that we have a kind of good exposure to this manual and to know the best practices that are being provided by this manual. AISC's Steel Construction Manual, the ASIC specification and numerous design aids in the form of tables and graphs. This is what really this manual is all about. It is giving us numerous design aids that is going to facilitate and help the designer a lot. And in the same time, it is going to be in a very easy to use tables or graphs that is very easy and very easy, and in the same time it is going to be very informative for us regarding the shapes and details of the cross sections and so on. So it is considered like a catalog of the most widely available structure shapes. Actually, we are going to use the 13th edition in our videos in general, and we are going to have focus on this edition because we have different editions, as we are going to see later. The editions of the manual, as you can see here, I found this picture, very interesting picture. It is maybe the first steel construction manual. I found it almost like it is, as you can see here, 1928. Maybe it's the first edition used here. And this is the latest edition, which is the 15th edition. So we have this is the 15th edition, the latest one. I think it has been released 2017. So actually there is story between these, between the first until the 15th edition. The first 9 editions of the manual and the accompanying specifications were based on ASD. So already we have talked about ASD and LRFD last time. So actually the first 9 editions, they were related to the ASD. However, the 9th edition was followed by editions 1 through 3 of the LRFD based manual. So there were 3 editions titled with LRFD based manuals. So now we have 3, and we have the 9th, so we have 12 editions that is related. 9 of them was related to ASD only, 3 of them related to LRFD, or they considered to be LRFD based manuals. And after that, the edition that followed, which for the first time incorporated both ASD and LRFD, was named the 13th edition because it was the 13th manual that had been published. So now the 13th edition is considered to be the first edition that is containing ASD and LRFD together. After that, we have the 14th edition, also covers both ASD and LRFD. And then the latest one up till now, we are having the 15th edition Steel Construction Manual, first released in 2017, and it is considered to be the most current edition here, the latest one that we are going to see in the market now. But as I said, that we are going to focus in our videos on the 13th edition. So this is going to be like our focus, and we are going to use it. And the difference is actually not that big in general, because the basics are going to be the same even through the earlier editions. But and we are going to always adhere and attach to the basics as much as we can in our videos. And whenever there is something that is different between one edition to another, or from one specification to another, if there is an updates or something, we are going to mention and highlight about it. But in general, the basics are going to be the same, and we are going to understand that there is one main thread that connects all these editions together. Okay, now let's go to have an exposure to the parts of the manual. So we have part 1 of the manual. Actually, we have like many parts of the manual. So every part is dealing with one particular like side of steel members in general. So for example, part 1 of the manual, it is titled Dimensions and Properties. This part contains details on standard hot rolled shapes, pipe, and hollow structural sections, HSS, including all necessary cross-sectional dimensions and properties such as area and moment of inertia. So this part, from its title, it is dealing with the dimensions and properties. Whenever that you are searching for the dimension and properties of any cross-sectional or any cross-section that you are going to use in your design, then this part is going to be of a great interest and is going to be important for you to refer to it. And it contains many structural sections, as we can see. Part 2 of the manual, it is general design considerations, and this part includes a brief overview of various specifications, including a detailed discussion of the ASIC specification. That's a very important thing. Whenever that you want to go through some of the specifications and some of the very useful discussions, you can go to this part. Codes and standards. So it has like including, as I said, detailed discussion of the ASIC specifications, and in the same time it is having brief overview of various specifications and codes and standards, some fundamental design and fabrication principles, and the discussion of the proper selection of materials. That's very important also. And then this part also lists the load combinations. As we said before, load combination, whenever that the specific material code like steel, for example, or if we're talking about concrete, ACI or something, they are referring to ASCE. So in general for load combination, but sometimes the code or the manual prefers or give some hints about usage of some specific load combinations in ASCE. For example, load combination with overstrength, you're going to find for example, special moment resisting frame, maybe they are going to suggest to use a specific load combination over others. So whenever that we're talking about load combinations, generally we should refer to this part, which is the load combinations that is listed by the manual. And of course, there is a relation with the ASCE 7. After that, we have part 3 of the manual, which is going to give us design of flexural members. So from its title, this part contains a discussion of specification requirements and design aids for beams in general. So beams, this is including the composite beams in which steel shapes acts in combination with reinforced concrete floor or roof slab, and plate girders. So we have like beams means that we have composite beams and we have plate girders. And part 4, it is going to be dealing with compression members in general. So part 3, remember this, part 3, it is flexural members, like beams, and part 4, it is going to be design of compression members. Part 4 includes a discussion of the specification requirements for compression members and numerous design aids. Actually, yes, numerous design aids are going to be found. And there's part for composite columns consisting of hollow structural sections or pipe filled with plain unreinforced concrete are also included in this part. Okay, and after that, part 5 of the manual, it is design of tension members, which is our main topic for today's video. This part includes design aids for tension members and summary of the specification requirements for tension members. So it is very important when we are designing our tension members. Part 6 of the manual is titled Design of members subjected to combined loading. So it means that it has the combination of loading, members that is having combination of loading, like having axial tension and flexure, or combined axial compression and flexure, or combined torsion, flexure, shear, and or axial force. So these are different combinations that we have regarding this part. This part is very rich actually in terms of the straining actions or the members that is having different and combined straining actions. Of particular interest is material on combined axial compression and flexure. Definitely this is one of the greatest part that we like to have, because many of us are, whenever that you are going to design, you're going to find that this combination, axial compression and flexure, is going to be like the dominant straining actions for many of elements or components, especially for columns, for example. So that's why it is very like important and crucial actually for our design. Then parts from 7 to 15, you are going to find that parts 7 through 15 cover connections in general. So we're going to find part 7, it is design considerations for bolts, and part 8, it is for welds, and part 9, it is related to connecting elements, that is related in general to connections. Part 10, it is design of simple shear connections, and part 11, it is design of partially restrained moment connections, and part 12, design of fully restrained moment connections. So we have two types of connection. Maybe we're going to touch upon this. We have partially restrained and fully restrained. And then part 13, design of bracing connections and truss connections. And part 14, design of beam bearing plates and column base plates, anchor rods, and column splices. Part 15 is going to deal with design of hanger connections, bracket plates, and crane rail connections. So they are dealing with, as you can see, with connections. And then we are going to find that specifications, here it was from 7 to 15, then for part 16 of the manual, specifications and codes. We call it specification and codes, and this part contains the most reference or the most important part of the manual, which is related to the ASIC specification and commentary. A specification also for high strength bolts, and AISC code of standard practice. So we have the most important part here is the ASIC specification, AISC specifications and commentary. This is very important for you. You are going to refer to it many times while you're designing. And then part 17 of the manual, miscellaneous data and mathematical information. This part includes properties of standard steel shapes in SI units and SI units, And also we have convergent factors and other information on SI units. And we have weights and other properties of building materials. And we have mathematical formulas and properties of geometric shapes. So these are the 17 parts of the manual, and I think that every part of it is important for us to deal with. But you're going to find yourself referring to frequently to some parts. Okay, whenever that you are going, for example, part 1 is going to be one of the greatest parts that you're going to refer to. Flexure members, of course, if you're talking about beams and columns. Part 6 of the manual, you are going to find that you are going to use it frequently. And then, of course, part 16, because it is related to the specification. So I think that these parts are going to be frequently visited during your design of the steel components and elements. Okay, now let's go to a couple of slides that is talking about hints about the manual, and they are important also. All design aids in the manual give values for both ASD and LRFD. So we are going to find that the manual is giving us values for allowable strength design and load and resistance factor design. So both are equally in the manual. They are dealt equally in the manual. And the manual uses a color coding scheme for these values. So whenever that you are going to deal with ASD allowable strength values, which is nominal strength over the safety factor, are going to be shown as black numbers on green background. Maybe you can, if you have the manual with you, are going to find something like this, black numbers with the green background, while LRFD design strength values, which is phi times Rn, are shown as blue members on a white background. So you are going to distinguish between the two based on this color coding color coding scheme of the manual. Another important couple of hints regarding the manual, that the AISC specification is only a small part of the manual. Take care that we are talking about specification, which is, as we said, part 16, and we're talking about manual, which has, as we have seen, like 17 parts. Okay, many of the terms and constants used in other parts of the manual are presented to, look to this sentence and take care of it, to facilitate the design process and are not necessarily part of the specification. That's very important hint here. Okay, not everything that you are going to see in the manual is considered to be a section in the specification that considered to be obligatory, for example, for us. No, it is only for facilitating. Many of the terms and constants in the manual are presented to facilitate the design process and are not necessarily part of the specification. In some instances, the recommendations are only guidelines based on common practice, not requirements of the specification. That's very important. Although such information is not in conflict with the specification, it is important to recognize that what is requirement means that related to the specification, a specification that is adopted by a building code, and what is not. Because based on this judgment, you are going to say, this is specification or a code term that I have to follow. There is a sense of obligation here, okay? Or like it's compulsory to follow, if you want to say. But for the manual, it gives you like some guidelines based on the common practice, okay, and the best practices. As a companion document to the manual is said, so these two hints, I'd like to say that they are very important to keep in your mind whenever that you're dealing with the manual. Okay. There is a companion document to the manual. A set of design examples is available at AISC website. These examples illustrate the application of the specification and the manual. A comprehensive building design example is also included. You can visit the website and you're going to find this manual is very useful actually, that you're going to find they are putting the LRFD and ASD solutions for every problem like in a side-by-side format, and you're going to get benefit from it. Numerous examples in every almost every element that you could encounter in your design profession. So it is very and highly recommended for you to have a look on this examples manual. Okay, and there is inside it, there is a comprehensive building design example. This is very nice. Comprehensive means that it's detailed building. A whole building design example is also included. So we're going to find beams, columns, connections, everything. So both LRFD and ASD solutions are presented in a side-by-side format. Okay, now let's jump to introduction to steel members. In general, we want to highlight this part, which is the introduction for us. Okay. So for steel tension members, we have like different different structures that is going to use the steel tension members. They are very useful actually in many structures. So you're going to find, if we have truss members, for example, they are used as truss members. Like they are used as bracing members whenever that we have buildings and we have cross bracing or so. They are used in diagonal members and elevated tanks. You are going to find these members, which are in red. They are tension members. In general, if we have lateral loading here, it is going, this structure is going to be, this column is going to be in tension and this is going to be in compression. We use them also as members in transmission towers. They are going to find, if we have wind or so from the side of the building, we're going to find that many of this transmission tower are going to be steel tension members. Okay. Hangars in buildings. Many buildings, they are like having, if we have canopies and so on, we are going to find hangars. They are going to be used there frequently. Hangars in bridges, whenever that you see a bridge, you're going to find that sometimes some part of the bridge is hanged over others. So this is what we call it a tension member also, that is bringing or linking the two parts together. Okay. If we're talking about truss members in bridges, if you look to any truss member, of course, in truss members we're going to find tension members, whether the cords or some bracings. Cables and cable stayed bridges. So these cables are tension members. And cables in suspension, that is, if you are going to find these types of cables, you are going to, these kind of bridges, you're going to find that the main cables here, they are under tension, and the suspenders, they are going to be tension members. So in general, structural elements that are subjected to axial tensile force, we are going to like title or give them this name, steel tension members. Okay. They are structural elements that are subjected to axial tensile force. There is no compression, of course. There is no flexure. There is no other types of loading or straining actions should be there. Only pure tension. The member should always undergoing tensile stresses, like forces making the tension on both sides. Application to structure, as we said, truss members, cables, and suspension and bracing for structures. Okay. Now let's go to the the cross sections of steel tension members. The sections in general, we have different sections. Okay, different types of sections. We have rolled shapes. Okay, so as we have discussed before, maybe we have hot rolled shapes like wide flange, standard, S shapes or wide flange, pipes, tubes, T's, channels, angles, and built up sections. Maybe it's not only one section, but built up section. As you can see here, we can like build like from two channels and two plates, we can put or make this cross section. Pin connected links and eye bars. So sometimes we use links and we need to use and connect them with eye bars, something like this. So this is the eye bar, and this is to another 2 eye bars, and here there is a pin, and there is hanger assembly here that is going to make this connection to work and tension. Threaded bars are going to be one of the sections commonly used. Cables, as we have mentioned, for bridges and other usages. The most common built-up configuration is probably double angle section. As you can see here, double angle section is considered to be one of the most commonly used cross-section for tension members. Because the use of this section is so widespread, tables of properties of various combination of angles are included in the ASIC steel construction manual. So you're going to find that a wealth of information in the manual regarding this double angle with different orientation, for example. Okay. Now let's go to the next, which is the connection of the tension member. Commonly we have bolted connection. Sometimes we have also welded connection. Many times also we have welded connection. But in general, what we are concerned with in the bolted connection, if you see, this is like a gusset plate and it is connected here, and this is the tension member, and we have the force, the tensile force is being applied on the member here. If you look here, you're going to have, or to see that we have two sections here. One section that is passing through the holes of the bolts, and other one is passing through the cross-sectional area of the member. So whenever that we look to this cross-sectional area, which is section AA, for example, we're going to find it here. It is this is what we call it the gross area. If we're talking about the plate here, there is no holes here. But if you are going to take the section here BB, you're going to find that there is holes of the bolts are existent. So this is because actually the stresses that is going to be developed in the gross area, we're going to deal with it in a certain way, or we're going to put some limits for it, and those are going to be developed on the net area. They are going to be dealt with in a different or considering another type of limit state. So tension members are frequently connected at their ends with bolts as illustrated. This is with bolts, and also we have welded connections, as we are going to talk about. The only determinant of strength is the cross-sectional area. Means that here the cross-sectional area is going to be the only determinant of the strength. It's different than compression members, for example. Compression members, you're going to find buckling, okay? Something related to the stiffness of the element itself, the end conditions of the element, and so on. Here, for the steel, it is very easy and straightforward for us. I mean that for tension members, easy and straightforward. Only the tensile force is going to be applied. Tensile stresses are going to be the main straining actions. And in the same time, the cross-sectional area, whether it is the gross area, net area, or effective area, they are going to be the only determinant for the strengths of the member. Holes influence design strengths, of course, because as we said that we have the net area here, which is the gross area minus the holes area. The net area, it equals to the gross area minus the hole areas. In general, analysis is direct procedure. Whenever that we are making the analysis, it is a direct procedure. But design is an iterative process. Take care of this, because the design is always an iterative process and may require some trial and error, because we are going to assume a cross-section for the element and then check the loading again and check the stresses and compare it with the allowable, for example. Okay, so it is like a trial and error process. Tension members are covered in Chapter D of the specification. Take care, Chapter D of the specification, not the manual. This is the specification, which is part 16 of the manual, and you are going to find it under Chapter D. Requirements that are common with other types of members are covered in Chapter B, design requirements. So you are going to find that the main requirements for designing steel tension members, you are going to find that it is covered in Chapter D and Chapter B of the specification. Okay. Now, Let's have a look on some of the building. This is, for example, as I said, this is the tension members here. As you can see also here, these are like hangers here. This is, as we mentioned, let me remind you, if we say that in cables and cable-stayed bridges, as you can see here, and we have the main cables here, okay, and suspension bridges. So this is what we can see here and here. In buildings, you are going to see some bracing, something like this. Whenever there is lateral load, for example, here, definitely these bracings are going to be under tension. Here also, stadiums, like warehouses, and so on. They are these are like tension members used commonly in the construction. Okay, as you can see here also. Okay, this is temporary steel structures, even that, or yes, you can see that we have like tension members all over, especially hangars, for example, in airports and so on. They are also like tension members. Here, as you can see, hangars and cables are used, especially in stadiums and so on. These are different structures with different ways of utilizing the tensile or tension members. As you can see, very interesting building here. As you can see, these are like considered hanger elements, and they are under tension. Space trusses, we are going to find that members, some of them, they are going to be under tension. Here also space trusses. Bracings in buildings, commonly we are going to find these bracing are designed for tension if it is the controlling and dominant straining actions. Here also, here in this building, as you can see, this is bracing elements. As you can see here also, this is might be under tension here also. And different shapes and different buildings, as you can see, they can be utilized almost in every type of building. As you can see here, bracings also. Okay, so these are different types of the buildings. Now let's go to the tensile strengths and how we are going to understand the behavior of tensile or tension member at failure mode. Now, first of all, we need to understand what are the failure modes of tension members and what are the expected failure mode of the connection of the tension members. So first of all, before going into the details of limit states and the design and so on, we need to understand what are the failure modes, how the tension member is going to fail. So broadly, we can categorize this related to, or we can categorize it and put it into two main categories. The first one is related to failure to the tension member itself, whether by yielding of the gross area of the member or fracture of the net area of the member at the hole and the bolts area. So this is related to tension member failure, the member or the tension member itself. Other type of failure is related to the connection of the tension member, okay, which is the connection itself. So we have like something related to the connection or at the area of the connection. We have like the block shear failure, for example. This block shear is going to be like a failure mode that is going to take place. Even that it's going to take place in the element itself, but it is near to the connection. So we consider that it is related to the connection because it has a combined shear and tensile failure modes together. Here we have the failure of the connection itself because the member is connected to the main structure using gusset plates, for example, some bolts. So maybe the bolts or maybe the gusset plate is going to fail. So this is what we call it failure connection or connection failure. So broadly, we can categorize the failure of tension member into two main categories. One related to the element itself, another one is related to the connection. Okay, and we are going to talk about each one in detail, so do not worry about this. So we have yielding of the gross area. This gross area is T times B if we are talking about the width and thickness. We have block shear failure, and we have the fracture of effective net area as we are talking here, which is the net area is going to be AN, which is equals to T times B minus D, where D is the area of the holes, or the holes area that is going to be subtracted from the main width, and failure of connection as we mentioned before, whether the shear and bolts, for example, or gusset plate rupture or something. Okay, now let's go to the failure mode of tension member itself. So we're going to talk about the tension member. So we are going to talk about the member itself, the first level of failure that we are expecting. In this case, we have a tension member. We can say a tension member can fail by reaching one of two limit states. So we have two limit states here. First limit state, we call it excessive deformation. And the second limit state is fracture. And take care of the wording here because it's really relevant and important to understand it. Remember that in the first limit state, I didn't say yielding of the material. Okay, I said excessive deformation. And in the second here, limit state, I obviously said fracture only. Okay, I didn't say anything else. So fracture, it is related to the material itself. Excessive deformation, it is related to the element itself, and we are going to understand what is the meaning here. So to prevent excessive deformation, if we have an element and this element under tension, if we are afraid of the excessive deformation or elongation of the element under the tensile force, then initiated by yielding, it is going to be by yielding. So excessive deformation would not take place, won't take place unless there is yielding occur in the gross section of the element. The load in the gross section must be small enough that the stress on the gross section is less than the yield stress F yield, right? So the load on the gross section must be small enough that the stress on the gross section is less than the yield. We need to guarantee that the stresses in the gross section will not exceed the yield, because if it would exceed or reach yield, then we are going to have excessive deformation. Okay, this is number one. And number two, to prevent fracture, okay, the stress on the net section. So take care of this, that in the excessive deformation limit state, we were talking about gross section, which is in the middle, for example, of the element. However, whenever that we are talking about the fracture, the stress on the net section, we are talking about net section. Where is the net section? Let's go back here. Here, this is the net section at the bolts area. Okay, at the bolts area. So in this case, net section is going to be our concern. Fracture is going to be our main limit state here. This is why we use in the first excessive deformation, we are going to use F yield, the yield of the material. Okay. However, in fracture, we are going to use the rupture of the material, which is Fu. Okay, it is going to be Fu. Sorry for this. It is Fu in general. Okay? So take care of this. Excessive deformation related to the F yield. Fracture, it is related to the F ultimate. Okay. Okay. So the real limit state of the excessive deformation, let's go deeper and understand it. Although yielding will first occur on the net cross-section, the deformation within the length of the connection will generally be smaller than the deformation in the remainder of the tension member. That's very true, because maybe you are going to ask, if we are putting the forces, the tensile forces here, and you are checking the yielding of the gross section, definitely, without a doubt, yielding will occur here at the net area before yielding would reach, or the gross section reach yielding. That's right, because here we have less cross-sectional area. Here we have the gross area, right? So definitely yield would occur here before here. But actually what we are dealing or what we are interested in is the excessive deformation. This means that if there would be a kind of yield at this connection length, we are going to accept it. This means that why we are going to accept this yielding here? Because its length is very small. And the excessive deformation or the deformation that is going to take place due to the yielding of this connection area is going to be small. Delta L is going to be very small if yielding of the net area is being reached. However, the main problem is in the gross area. In the gross area, if yielding reached here, or the gross area reached the yielding, this means that the strain times L. L here, it is going to be the total length of the gross area, which is almost the length of the element. So E times L, this means that it would give us delta L here. Delta L due to yielding of the gross section is much larger than delta L due to the yielding of the connection area or the net area. So this is why we do not care too much about yielding on the connection area or the net area, because it will make small excessive deformation. However, here for the gross area, the length is very high, so the strain times the total length is going to give us very high delta L. Here delta L, for example, might reach, for example, like let's assume that 10 centimeters. Okay, I'm sorry for this, 10 centimeters. Okay. However, here for delta L might reach only like 0.9 centimeters. So we are not interested in this. This is very small, 9 millimeters, but here it is going to be 100 millimeters. Okay, so this is excessive deformation that we are fearing from. The reason is that the net section exists over a relatively small length of the member, and the total elongation is a product of the length and the strain, right? A function of the stress, as I explained. Most of the member will have an unreduced cross-section. So attainment of the yield stress on the gross area will result in larger total elongation, as I said here, because the length, as we said, most of the member will have unreduced or an unreduced cross-section, means gross section. Okay, so it is this larger deformation, not the first yield, that is the limit state. That's very important here. If we go back to this, we said excessive deformation, as I said. I didn't say yield, because actually if excessive deformation is going to take place in the gross section, definitely the net area already has experienced the yielding. Okay, so that's very important note here, that is, it is larger deformation, not the first yield, that is the limit state. I hope that we could understand it very well. Now let's go to the real limit state for fracture. What will happen here? So first of all, existence of holes causes stress concentration. Whenever that you have a hole here, you're going to find that there is stress concentration at the edges of the hole compared to the gross area average stress, right? Local yielding occurs around the hole. Of course, that is at this point here and here, local yielding would occur. And we found that almost F maximum, the maximum stresses that is going to take place at the edge of the hole is going to be 3 times F average, which is the average gross area stress. Fracture on the net section is going to be F maximum, so we are going to compare it with F ultimate. Here it is going to be brittle failure. Here we are going to experience fracture of the material at the edges. Okay, we're not dealing with yield now. Okay, so in reality, stresses at holes can be as high as 3 times the average stress on the net section. As you can see here, it is 3 times almost F average. And at fillets of rolled shapes, they can be more than twice the average. If we're talking about fillets of rolled shapes, okay, then they are going to be twice of the average. Okay, so because of the ductile nature of structural steel, the usual design practice is to neglect. Take care of this word. It is very crucial here. Is to neglect such localized overstress. So the overstress here is going to be neglected and intentionally. After yielding begins, look to this, why we are neglecting, because after yielding begins at a point of stress concentration, so if we say that at this very edge point here, yielding is going to take place. What will happen? This yielding here is going to distribute some of the loading or some of stresses to the adjacent strips. Then the yielding is going to be relieved, or the high stresses here is going to be reduced because of the redistribution of the load. So this very high point is going to be reduced because it is going to give to the other strips here. Okay. After yielding begins at a point of stress concentration, additional stress is transferred to adjacent areas of the cross-section. This stress redistribution is responsible for the forgiving nature of structural steel. So if we say that it is a little bit like counterintuitive whenever we say that, well, yield is going to take place here. Why we are going to talk about like fracture or something like this? Why we do not start with yielding? Okay, so the point is the right answer for this question is yielding is going to be reached, but the point is we have a ductile nature of the structure steel that is going to make redistribution, okay? Redistribution of the stresses. So the highly stressed section is going to give to the lower stress section, okay? So we can put it like this and remember it very well. Its ductility permits. The ductility of structural steel permits the initially yielded zone to deform without fracture as the stress on the remainder of the cross-section continues to increase. That's right. So this is the ductility. It's very, very important characteristic of steel. You're not going to find it in concrete, for example. Okay? So this is why it is a very unique characteristic for this particular material, which is steel. Okay, so under certain conditions, however, but we need to take care that under certain conditions, steel may lose its ductility. So that's the key here. Ductility may be lost, and stress concentration can precipitate brittle fracture. These situations include fatigue loading and extremely low temperature. So we need to take care of these two dangerous situations whenever we're talking about fatigue, which is repeated cycles of tension and compressions, okay, and whenever we are talking about low temperatures. So steel is going to lose its unique characteristic, which is ductility, in these two conditions. So we need to take care of this. So if you are going, for example, if you are going to design a vessel that is going to go to very cold area, then take care that do not go with this limit state, because you are going to find ductility would not work for you. If there is a small hole, maybe it would cause the failure of the entire element. And whenever that you are making this for example, for bridges or for elements that is going to have a repeated cycles of tension and compression, fatigue is going to be determinant for this element. And ductility is not going to work for you in this case. It is not going to be in your favor to assume that this redistribution technique that we were talking about. Okay, I hope that you understand this very well, because it's very important whenever you design your structure to understand where that you are designing this component or element. Okay, now let's talk about generally about the ductile and brittle failure of tension members. If I ask you here, we have two limit states. If I ask you here, which one is going to be better? If I'm going to ask you as a designer, and you have the excessive deformation limit state and the fracture limit state, which one that you're going to use, or which one that you're going to like select to say that I want my element to be or to fail using or based on excessive deformation or fracture? Just think for 1 or 2 seconds before answering. So the answer is here. We found that whenever that we are dealing with the tension members, if we are making a relation between elongation on the horizontal axis and force in the vertical axis, and we plot the behavior of the tensile or the tension members, we found that yielding of gross area is going to be traced or plotted with the blue curve, and the fracture of the net area is plotted in the red curve, as you can see. We found that something that is very interesting, and actually it was expecting also. Yielding of gross area is showing a ductile behavior. Ductile behavior here for the yielding of the gross area. However, the fracture of knot area or connection failure, we found that it is having a brittle behavior. So as a designer, we always like the ductile behavior. We do not like this brittle behavior. Strength is going to be limited, and also ductility is going to be limited. So we like to choose this limit state, excessive deformation limit state, not fracture. Okay, even in the design, you are going to find that we are, as we said, we are going to here we are going to use F yield. Right here, we're going to find that we're going to use F ultimate, excessive deformation because of yielding the resistance factor, and LRFD we're going to use 0.9. Here we're going to use 0.75, the fracture, as we're going to see in the design procedure. Okay, this is for LRFD. Okay, and even for ASD, we're going to find that here we're going to use safety factor like 1.67, for example. Here we're going to use safety factor of 2. So this means that this limit state is preferred over this limit state, or this failure mode is preferred over this failure mode. Okay, so now we understood what is the meaning of ductile and brittle failure for our limit state and which one is preferred over the other. Okay, so yielding, as I said, yielding of gross area is most desirable. Okay, and something I didn't say, residual stresses cause early yielding. Residual stresses during the manufacturing process and so on, this is going to cause early yielding for our members. So we need to consider this and take it into consideration as well. Okay, behavior of tension member with bolted versus welded connection. Which one is better for us? Which one is going to be better, bolted or welded connection at the connection part? If we are plotting the elongation versus force for two different types of connections, we have here the blue one. It is the tension member with welded or riveted connection. Actually, welded and riveted, they are like very, even that riveted means that seemingly to be like bolts here, but rivets, they are like making the connection or making the tension member and the gusset plate like working as if they are welded. Okay, so this is why we put them in the same category. This is why they are very well, very suitable for places where that vibrations are there, for example, because there is no relative movement between the gusset plate and the tensile or the tension member. However, for tension member for bolted connection, as you can see, it's in the green, for example, green curve. As you can see it here, that we are experiencing something that is, in the beginning, they are both the same, but at one particular point, we found that maybe the bolted connection would experience what we call it slippage of bolted connection, that the connection at the bolted connection is going to have slippage phenomenon here. So this would shift this curve to the right, and you're going to find that it has less strength And maybe the ductility is higher, but actually this ductility is going to be in the excessive deformation part. So it is not useful for us in general. Okay. So anyway, this is the comparison of tension members with bolted and welded connection. And if we say also that if we want to say that what is the main reason, maybe slippage, which is maybe high strength bolted connection can slip also. So this is something that we need to take care and put in our minds. Okay. Now let's go to the LRFD design strengths and then followed by the ASD design strengths, how we are going to design. Then for the design strengths for LRFD, we are having, as usual, as we have explained before, we have the nominal strengths in yielding, and we understand why we're talking about yielding. And whenever that yielding is being mentioned here, this means that, yes, gross area is going to be used. And whenever that nominal strengths in fracture word is used, this means that we are going to use exactly area net or area effective. We are going to distinguish between the two maybe in the next video. Okay. And whenever we say yielding, this means that F yield, of course. Whenever we say fracture, we are using the F ultimate of the material. So the multiplication of the two would give us the nominal strength, tensile strength of this member. And resistance factor, this is the strength here, the design strength for us. And for the resistance factor, as I said, whenever we use yielding, okay, it is going to be 0.9. Phi is going to be 0.9. This means that we are reducing 10% only from the yielding, nominal yielding, from the yielding of this material. However, fracture, phi or phi is going to be 0.75. Why this kind of 0.9 and 0.75? So we can say the resistance factor phi is smaller for fracture than for yielding, reflecting the more serious nature of fracture. Reflecting the more serious nature of fracture. And we are going to have the minimum of that our P ultimate should be less than or equal to 0.9 F yield A gross or area gross. And here P ultimate should be less than or equal to 0.75 F ultimate AE. As we said, the effective area is the effective net area, which may be equal to or either the net area or in some cases a smaller area. Okay, we are going to give more details about it in the future videos. Okay, so we are talking about the minimum. Okay, what is the minimum? If the material is going to yield, for example, gross area is going to yield at, let's assume, under 100 kilonewton, okay, and our fracture is going to take place at, let's assume, 90 kilonewton, then our design is going to be 90. And our design, I mean that our design strength is going to be 90. And if the member reaches 90, there would be fracture at the net area. But if we say that it was not 90, it is 120, for example, this means that our section is going to be, there is yielding in the gross section, and our element is going to fail when it reaches 100, and this is due to excessive deformation. Okay. Now for ASD design, it is as common as we have explained before. We are going to have PA. Okay, so the letter A here means, okay, so the subscript A indicates that the required strength is for allowable strength design. But you can think of it as standing for applied load. So you can think about it like this: A, applied load, or allowable strength design. Okay, it's the allowable load. It should be less than or equal to Pn, which is the nominal strength over the safety factor that we're going to have, omega. Okay, in allowable strength design, the total service load is compared to the allowable strength allowable load. Pa is the required strength applied load, and Pn over omega is the allowable strength. Okay, And here for yielding of the gross section, the safety factor phi t is 1.67, and the allowable load is, this is as we know here, Pn is going to be F yield times area gross over safety factor. Okay, this gives us 0.6 F yield area gross. However, for fracture, we are going to have Pn here. It is going to be F ultimate times AE, effective area, which is, as we said, net area, or maybe smaller, over the safety factor 2. We understand now why this is 1.67, why this is 2. Okay, 2, it reflects the serious nature of fracture, as we said. The fracture of the net section, the safety factor is 2, and the allowable load is, as you can see, this is the allowable load. Okay, now we understand very well how can we design using ASD or LRFD. The last slide here in our video for today, we're going to talk about from where we can obtain F ultimate, F yield, and F ultimate from in the manual. So from where we can obtain them. So F yield and F ultimate can be found in table 2-3 in AISC manual. So you can find this table, which is table 2-3, called applicable ASTM specifications for various structure shapes. We're going to find 2 columns here, F yield, minimum yield stress. We're talking about minimum yield stress in KSI. And the other column is F ultimate, the tensile stress in KSI also. We're going to find them here. Commonly, we are going to use A36, ASTM designation A36, okay, which is carbon steel. Commonly, also, we are going to have A572, A572, which is high strength low alloy, okay. And also, we are going to use A992, which is also high strength low alloy with these different F yield and F ultimate characteristics. We're going to find that a bunch of designation for it, A572 grade 42, 50, 55, 60, 65. So it is based on the grade we can find the minimum yield and the corresponding tensile stress and so on for all of them. These are the most commonly used ones. You are going to find that in the table in the right, you're going to find applicable shape series, which is the preferred material specification for each type of sections. Wide flanges, miscellaneous, which is M, standard shapes, HP, C, which is the channels, miscellaneous channels, or angles. Okay, and then we have hollow structural sections, whether it is rectangle, rounded, and then at the end we have the pipe. So the black ones here, the color coding here, this black ones, it means that the preferred material specification for the design or manufacturing of this shape. So for example, for wide flange, this is going to be the preferred material specification for it. And the gray one, it is other applicable material specification, the availability of which should be confirmed prior to specification. So this is the coding color here, and the white is material specification does not apply. Okay, so we have these 3 different color coding for this table we need to understand, and from here we can get our F yield and F ultimate. These are the types of the shapes that we have explained before, W, M, S, H, B, and so on. You can find the designation here in general. So as we have mentioned in the previous video, like wide flanges, for example, it is like which have essentially parallel inner and outer flange surfaces. M shapes, which are H-shape members that are not classified in ASTM. A6 as W, W, S, or HB shapes. M shape may have sloped inside flange, face, or other cross-section features that do not meet the criteria for the wide flange, S, or HB shapes. So this is the meaning of M here. Okay, the others you can read it in the manual. I think this is the last slide in our video for today. I hope that you have understood what I have explained today, It is very interesting journey in the tensile stresses and tension members, failure criteria and mode shapes and so on, mode failures. And I think that we have gone through many things related to our tension member design philosophy. I hope by the end of this video you could understand more. Next video I'm going to talk about some examples of tensile strength. So I'm going to explain about 3 main examples for tensile strengths related to the angle and plates and double angle. Thank you and see you in the next video.